Hey everyone, so welcome to today's session on current and charge. Here we'll be just taking 1 second. So thanks everyone who's managed to come out as always on a Sunday. So, okay, I'll tell you a bit about how today's session is going to work. So we're going to be reviewing current and charge. We're going to do it as a lesson. So that means we're going to split things in two parts with an introductory slide. So in our introductory slide, we'll just give you a couple of reminders of the things that will be useful to know for as like background knowledge for today's session. And then in each half, we're going to learn some new stuff about current and charge. And once we've learned that new stuff, at the end of each half, we'll do some exam questions to make sure that we're kind of understanding what's going on so far. If you have any questions at all about any of the stuff that I'm going through, I'm looking at the chat as I go through the session, so please just ask them. I'll keep my eye on it. And as long as it's in scope of the lesson and we have time, then I will do my best to answer any questions you have. The more questions that you ask about anything you're confused about, the better. Helps us to understand, what's landing and what's not. So that would be great. Also, I might ask questions as I go along. If I think it would be useful to see what people's responses are. Doesn't matter if you get the question right or wrong. The important thing is to have a go. So feel free to type your best guess or your answer to any questions I ask as we go through, and that'll be helpful to everyone. Okay. So we'll just give people another minute or so to filter in. So today is for the three main exam boards, AQA, OCR, and Edexcel. We'll take a look at the spec points. There's actually a bit of this session which I think is not on spec for AQA, but we'll check that when we go through the slides that say which specification points we're going to be doing for each of those main exam boards. Okay, so hopefully that's making sense. And yeah, okay, so if you have any questions, as I said, just let us know. And in the meantime, I think that we're in a good position to just get started. Okay, so as I said, today is current and charge. So let's go. And just very briefly about me. I look a different there. That is indeed me. So I'm Matt W. I'm the lead physics teacher here at Snap Revise. I've been a physics PhD student at Oxford University and a A-level physics tutor for quite a long time now. Okay, so enough about me, and now about current and charge. So our objectives today are to define the terms charge and current. So this is quite a fundamental lesson. We're going to understand that charge is quantized. We're going to understand that charge is not the kind of thing that can be divided up forever. It comes in little chunks. And we're going to describe how current can be caused by the movement of electrons. In fact, current is the movement of electrons. Okay, so that's what we're going to learn about charge and current and their interaction. Good. And as promised, we should do a little review. It's okay if you haven't seen this stuff before, although I think it would be quite likely. Just a little bit to say where the charges that we're going to have in mind today come from, and they're fundamental particles. You can find them in the atom, and then a little bit about current and circuits. Okay, so just as we get started, there are three kinds of particles here. Let's say that I label the blue ones here as protons. This is a diagram of an atom. And I label the other ones as neutrons. What are the red particles? What's the name of the red particles? So we have protons in the center and we have neutrons in the center. So what's this hanging around the outside of an atom? It's the electrons. Good. And I asked you about this one because electrons are going to be the most important particles for today's session. So you're absolutely right. These are electrons. And as we're going to talk about in more detail later, we can say that protons are positively charged. We can say that neutrons have no charge. And then what would we say about electrons? So these are positively charged. These are neutral. That's why they're called neutrons. What about the electrons then? So the electrons are negative, and that's something we're going to talk about in more detail later. Good, absolutely right. They're charged negatively. Because these electrons are charged negatively and protons are charged positively, this balances out on the whole. We have two negative things on the outside, two positive things on the inside. So the atom as a whole is also neutral. And again, we'll talk more about that later. Okay, and that means that if we were to add or remove electrons, we would make the atom charged. And if we were to do that, we would be making what people call an ion. Okay, really good. Nice stuff. So now we're going to go away from focusing from a single atom or a single particle to something much more zoomed out. We're going to look at a whole circuit. A circuit is made of wires. Wires have got loads and loads of atoms in them, and they've got loads of free charges, as we're going to learn later, that move around them. So don't worry if that doesn't make sense for now, but just as a little overview, if this circuit element here is a cell, in other words, it's like a perfect battery, then I can label the longer end of this symbol with plus and the smaller end as a minus. And I can say then which way current is going to flow around this circuit. Again, we haven't introduced current properly, but that's just to get us started. And this current will always flow, whatever this thing is that's flowing, it always flows away from the positive side, goes round, and then into the negative side. Okay, good. And finally, can anyone say what this symbol is here? This symbol, I'll say what its purpose is. Its purpose is for measuring this weird flow thing that I'm talking about. It's there for measuring this thing called current, which I'm giving this symbol I. But what's its name? What's the piece of apparatus that we can use to measure current? Yeah, perfect. Absolutely right. The answer is ammeter. Good. So A here is an ammeter. Smashed it. Okay, good. Well done, everyone. So that's just a little review. We'll be doing some of this in more detail later, and we'll be doing some more complicated things too. So for the spec points, for AQA, most of what we say today will be relevant, but there'll be something we introduce later, which you can see in OCR and Edexcel, which is this stuff here. One sec, I lost my pen. This stuff here, which is about what people call the transport equation. And that special equation you won't need to know in AQA, but you will need to know, you see it popping up here as well, 41 for Edexcel. You will need to know it if you're OCR at Edexcel. Anyway, most of the session will be relevant to everyone. Just this transport equation a bit when we come to it. You don't need it for the AQA exam, but I think it's still extremely useful to understand it, and I think it will actually help you. So I recommend listening in anyway. Okay, so let's talk about charge and current properly, and we're going to right back to the start. And the problem with going right back to the start is that in science, you always have to explain one thing in terms of another thing. And so when we introduce charge, actually fundamentally, charge is really hard to explain because charge is this thing that causes interactions that we call electric interactions. And it can't be explained in terms of something else. It's just there. We've spotted it around. It exists and we can observe its behavior. So charge is one of these fundamental things that we explain lots of other things in terms of. Therefore, you're unlikely to be given a definition of charge. But if we tried to, here's the best attempt. Charge is an intrinsic property. And that just means it's not something that we're going to explain in terms of something else. It's just this basic thing that we use to explain other things. So it's an intrinsic property of an object, which means we refuse to say too much about it. Okay. But there's some things about the kind of thing charge can be. And we're going to say right now, it's the kind of thing this charge thing, it can be positive. So it's the kind of thing that can be positive, negative, or neutral. So it can be positive, negative, or it can be zero. These are all options for charge. Okay. And when we see something zero, we often say that that means it has a neutral charge. And that basically means it won't be involved in interactions based on charges. It won't be involved in electricity at all. Okay. Now, because we have these two different kinds of charge, they have quite interesting behaviors. Okay, so what I want to say here. Well, okay, let's give the two rules. We can say that any charged object will be repelled. Whoops, we lost a pen. Will be repelled from like charges. So what does this mean? This means if I have a positive charge and another positive charge, they will push each other away. If I have a negative charge and another negative charge, again, they will push each other away. They will be repelled. Okay, the opposite is true for opposite charges. So if I have one charged object, it will be attracted to other opposite charges. This is A level, although I guess you may be asking because this is super fundamental and it's stuff you would have also learned in GCSE. As we go on, especially into the second half of the session, things are going to get much more specific to A level. Cool. Okay, good. So there's a last example. We have a positive charge, we have a negative charge, and these things will be attracted to each other. Good, that's this law here. And so just as a final example, if we have some negative charge here, and it's in between some collection of negative stuff and positive stuff, then because of this law here, it's going to be repelled away from the negative stuff. But also because of this law here, the attraction, it's going to be attracted to the positive stuff. So it's going to feel an even stronger force to the left here. One from this and one from this. Okay, good. So now we're going to talk about the quantization of charge. And that sounds like a horribly, that sounds like a complicated concept, but it's really not. Quantization to physicists just means comes in bits, comes in chunks, can't be divided into smaller and smaller bits forever. In other words, there is a smallest charge, which physicists sometimes call the quantum of charge. And this smallest charge is also called the elementary charge, because it's the most elementary, it's the most small. And it has magnitude E equals 1.6 times 10 to the minus 19 coulombs. Now, if I say, and I should say one more thing. What's this unit? Coulomb. Well, let's write it here. This is just the standard unit for charge. Whenever you declare a charge, whenever you declare any quantity, you need to state a unit. And here, the usual unit for charge is coulombs. If we call this number 1.6 times 10 to the minus 19 E, then protons have a charge of plus E. In other words, they have a charge of 1.6, blah, blah, blah. Electrons, however, are negative, and this is where that negative turns up as an actual mathematical concept. Electrons have a charge minus E, in other words, minus 1.6 times 10 to the minus 19 coulombs. Good. Now, the quantization of charge rule says that whenever something is charged, whenever something has a charge, it's because it has a load of extra elementary charges or a load of missing elementary charges. Therefore, any charge you see can be measured as an integer multiple of E. So what does this mean? This means that if something is charged, it's because it's got a surplus or lack of elementary charges. For instance, this object here has got 1, 2, 3, 4, 5, 6 bonus elementary charges. And so its total charge is 6E. You could also have other things that have 4E or 2E or 1E or 3E. But what you'll never see is a half E or 3/2 E or 1/4 E. Those you're not going to see. because those would require you to break up the elementary charge E into even smaller bits or fractions. And this is what is meant by this phrase, integer multiple of E. Whole numbers, those are integers, and so we have whole numbers multiplied by the number E here. Okay, so let's take a look at an example, just a little practice question. Does E stand for electron? It stands for the charge of an electron. E is a number that stands for charge. We give it the symbol E because we know that it's the charge of the electron. That's just something we do to remind ourselves what it is. But E is quite strictly just a number, and the number that it is 1.6 times 10 to the minus 19. Good. Okay. Okay, so we've got a question here. A neutral rod is rubbed with a cloth to remove electrons and give it a positive charge of 6.4 times 10 to minus 19 coulombs. Calculate the number of electrons it loses. Okay, good. Any ideas? What can we say here? We know the charge it has. Often, by the way, we give the symbol, the charge a symbol Q when we don't know what it is and when we don't know that it's E. But how many electrons make up that charge? Well, we have this total charge and we know that it's going to be some number times the charge of an electron, the elementary charge. So we can find out the number by just rearranging this. It's going to be 6.4 times 10 to the minus 19. And we need to divide by the charge of a single elementary charge, which is 1.6 times 10 to the minus 19. And then we'll get a really nice number. And the number we get is 4. And note, just remember, what we couldn't have gotten is 4.1 or 4.7. It would have to be a whole number. It's always going to be a whole number here of elementary charge. Okay, good. So today's session is about charge and current. We introduced charge. Now we're ready to introduce current, which is a concept that involves charge. Specifically, it's the rate of flow of charge or the rate of transfer. So electric current is the rate of flow of charge. And sometimes people say the rate of transfer of charge. Okay. So let's write this down as an actual formal equation. Just so you know, my degree was physics. Okay. And then mathematical physics. Okay, so now we need to turn this into an equation. Okay, the rate of transfer of something. Whenever you see a definition which says something is the rate of flow of something, that means taking change of that thing and dividing it by change in time. So what's this thing here I mentioned before? Charge gets the symbol Q in general. So this is a change, because delta means change, by the way. Delta, that means change. So this means change in charge over change in time. Okay. So the time will typically be measured in seconds. Charge is measured in this new unit coulombs. And therefore, this symbol here, which is the electric current, is measured in coulombs per second. But we have another name for that unit. We also call that 1 ampere, and we give that the symbol A. Okay, good. So yeah, I'll just say one more thing. I think a picture could be useful here. So here's a picture. Usually we imagine we have something called a circuit. So we have some wires and we have some kind of a device in the circuit. And we often think about drawing current as something that flows through the wires and say also through devices. And ultimately flows around circuits. And when we draw something like this, what we're really describing here is a rate of flow of charge. So there are charges over here. Let's give them a blue symbol. There's charges over here, and they are moving through the circuit, and that's what this current is. Okay, good. So let's have a go at a practical question. Calculate the current for a wire if it takes 18 milliseconds to transfer a 1.4 coulomb charge from one end to the other. Okay, so we only have one equation available to us at the moment. We want to calculate the current, and we have a formula for the current, so we should write it down. Formula for the current is its change in charge over change in time. Okay, and we have a transfer of charge, 1.4 coulombs, and we have the time it took for it to happen. Now, if I just write 18 here and then calculate the answer, what mistake have I made? What mistake is this? Why is this not going to give me the right answer for the current? Certainly, if I want the current at the end to be in amps. So you have to be very, very careful when you're reading a question like this to make sure you keep track of the units. So what are the units of this time that they've given here? Well, we need the time to be in seconds, but they've given us the time in milliseconds. So we have to convert this quantity to seconds. And so 18 milliseconds, exactly right. So 18 milliseconds is actually just 18 times 10 to the power minus 3 seconds. And now we're ready to use the equation. And now if we do it, we'll get 78 amps. Right, and we'll get the right answer. Finally, we mentioned this before, so I won't ask you again. The piece of equipment that you can use in a circuit to actually measure the current that is flowing through the circuit, that is called an ammeter. Meter, I think it's 2 amps. And we can just draw it as a circle with an A in it. Okay, really good. So, how are we feeling? That making sense? Do we have any questions? Okay, we got a 1. So I'll keep my eye out in the chat in case there are any questions. And in the meantime, I'll press on and we can do some exam questions. Okay, so in this first question, we're asked to define what is meant by electric current. And this is something I've already given you directly, so let's just talk about it. It is the rate of flow. Transfer would have been fine here too, remember? The rate of flow of charge. Nice, quick, easy mark. We love it. Part B. The SI unit of charge is the coulomb. Define the coulomb. Now, this is a really good question because it's a classic kind of question. And it's something that there's a pretty clear technique for answering. You might say, well, you know what the coulomb is. The coulomb is the unit of charge, right? Well, we can say a bit more to make sure we definitely get the mark. And there's a kind of system here. You want to find the kind of defining equation that the coulomb appears in. And they've already given us a clue here. It's the equation that involves current. So we have current equals charge over time, right? Change in charge over change in time. And so if we want to talk about Coulomb, which is about charge, we can rearrange this equation. Coulomb is current times time. And now that we have this like defining equation for the Coulomb, for the charge, sorry, then we can define what one unit of this is. We can define what 1 Coulomb is by setting the current to be 1 and the time to be 1. So, okay, now we can set this, now we can put this into a sentence. So this is charge transferred. That's what coulombs are about. And we can say it's the charge transferred when 1 amp of current runs for 1 second. So it is the charge transferred by a 1 amp current in 1 second. 1 second. Okay, good. So let's have a go at our next question. In our next question, figure 1.1 shows 2 strips of aluminium foil connected to a DC supply. Okay, and here's our DC supply. Okay, the switch S here is closed. Fine. And now we're told that the charge flow past a particular point in one of the aluminium strips is 340 coulombs in a time of 50 seconds. And we're asked to calculate the current in this strip. I would just remind people that I'm only going to be answering questions which are on topic for this session. Okay, only questions about this session. So now let's have a go at this question. And what equation should we be using, everyone? We want the charge flow past a particular point in a certain time. They want the current. So we want the defining equation for the current. What is the defining equation that the current appears in? Well, it says the current is equal to the change in charge over the change in time. Okay, good. So we have the change in charge. They say that we have 330 coulombs of charge moving through. 330. And then we have the time. The time is 50 seconds. So there we go. And now we can just chuck this in a calculator. And if we chuck it in a calculator, we will get 6.8. And that's measured in amps. Okay, really good. Hopefully that's all making sense. Just let me know if there's any questions. We have one more exam question for this half, and then we'll go on to talk in a bit more detail about the specifics of current. Okay, so part C. A digital watch uses a 1.3 volt cell. It delivers a charge of 650 coulombs at a constant rate during its lifetime of 1.6 times 10 to the power 7 seconds. Calculate the current delivered by the cell. Okay, everyone. So someone put in the chat, what equation should I be using here? Let's label these. We've been given a voltage. We haven't really thought much about voltage today, but that's okay. We've been given a charge. Usually we give that the symbol Q now. We've been given a time. They want to know the current, I. Once you've written these out, if you can see what equation we should be using. So what equation should we be using? Perfect. It's the defining equation for current. It always was going to be. I equals change in Q over change in time. Change in Q is 650 coulombs. The change in time is 1.6 times 10 to the power 7 seconds. Chuck that in a calculator and you'll get 40.625 times 10 to the minus 6. And so if you look at everything we've been given, it's to 2 significant figures. Let's give our answer to 2 significant figures as well. 2SF. Perfect. Well done. Okay. Next question. The total number of electrons passing through the cell during its lifetime of 1.6 times 10 to the 7 seconds. Okay, I think this is a good one to just pause and have a look at. Any ideas? What calculation should I do here? What should I divide by what? Total number passing through the cell during its lifetime. So you want to know the number of electrons. In other words, the number of E's. I want to know how many of those passed through. They've told us the time, they've told us the voltage, they've told us the total charge that goes through. Good. Really, really, really good. The total charge that passes through, telling you the exact time again, I think is a bit of a red herring. I think it's there to throw you off a bit, really. We know the total charge. It was 650 coulombs. And we know that is going to be the number of electrons that pass through times the charge of each electron. So we simply find the number by taking 650 coulombs, dividing by the charge of a single electron, which is 1.6 times 10 to the minus 19. If you do that, then you will get around 4.0625 times 10 to the 21. It's no surprise because we're dividing by 1.6 again, like we did here. So these numbers should look similar. Okay, good. And then the number of that number, let's say, what is that roughly? Well, that's roughly 4.1 times 10 to the power 21. And if you're worried that this is not a whole number, don't worry, because it's not 4.1, it's 4.1 times 10 to the 21. So that absolutely is the whole number. Good, okay, and that's the two significant figures again. Okay, so in the next part of this session, we're going to be talking about the motion of electrons. Now, you might think we already talked about that. We defined current, sorry. Current is the rate of flow of the electrons. But we can say a lot more if we actually zoom in on a piece of wire, that's where electricity flows, and look in more detail at how the electrons move. You might get from this idea of current as a flow of electrons that you've just got like a load of electrons in a queue, and they're all just steadily moving along uninhibited. And that is absolutely not how things are actually going on inside a wire. So let's talk about that now. So if you go back, again, it might actually be to some GCSE physics or chemistry. You'll have thought a bit about conductors and insulators and what they're made of. And you may well have been told that metal conductors, so metals, those materials, they're examples of conductors, and conductors are typically, or metals even, metals are typically these lattices of fixed ions with free electrons floating around them. And that's the picture that we're going to take now. And we're going to talk about current in terms of that picture. It's going to be more complicated. That's okay. So let's remind ourselves what a metal conductor is. A metal conductor, or any metal, a metal conductor consists of a fixed lattice of positive ions. Good. Okay, and we've drawn this down here. Here is our fixed lattice. In fact, let me label it in a more appropriate color. There's our fixed lattice. These protons are not going to move. They are fixed in place. Lattice is just a fancy word for like square or cube made of lots of regularly placed dots. Okay, good. That's just all lattice is a fancy name for. Good. Okay. And the other bit, if you were giving a chemistry answer about the structure of a metal, the other thing you'd have to say is that there's a lattice of positive ions, and then there are free electrons. Free electrons. And what do? Well, they are things which can move between the ions. Right, because they're free. There's the fixed lattice and then the free electrons. And the free electrons are free to move around the material. That's why they're the kinds of things that can carry current. However, if I just have a piece of metal in front of me and it's not connected to a battery or a current source or anything, I don't expect to see electricity flowing through it. It's just a lump of metal. And yet there will still be motion of these electrons. The electrons will still be moving. It just turns out they'll be moving randomly. And current is going to be about a net flow. So we'll come to that in stages now. So normally the motion in a general just slab of metal is as follows. Normally, the motion of the electrons motion of the electrons is random and has no average or mean average velocity. So what do we mean? Well, let's focus in on these electrons now, these red dots. Well, in principle, in just a slab of metal, who says what direction any of them should go? So this one might be going in this direction. 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 Okay, this is random motion. They're all going in weird directions. Let's put that one up there, that one up there too. Why not? Okay, good. Now, what are we saying about average velocity here? Well, to calculate the average velocity of all of these electrons together, let's say this is electron 1, electron 2, electron 3, we would add together the velocity of number 1, velocity of number 2, the velocity of number 3, and so on. Now, it turns out that this is going to be roughly 0. Why is it going to be roughly 0? Well, you can look at it's because it's random. So if you look at electron number 1 here, for instance, it's going down and to the left. Electron 2 is going up and to the right. And so they're going to cancel out. V1 plus V2 is going to be roughly 0. Because the motion is random, for each velocity you have going in some direction, there'll be something else somewhere that pretty much cancels it out. And so again, in general, your velocity is going to be roughly 0. So the motion is random. There's no net velocity. There's no average velocity of all these electrons. Now we're going to study the case in which we've connected this piece of metal to a circuit. For instance, this piece of metal could be a wire connected to a battery. So connecting something to a battery means connecting it to a charge difference. So when a charge difference is applied, electrons are attracted to the positive end. Why the positive end? Well, electrons are negatively charged, so they will be attracted to positively charged areas. Okay, so let's just draw ourselves a picture here. You see now we've drawn a negative charge over here and a positive charge over here. One way we could have created this is to take this thing, which we're imagining is almost like a big thick piece of wire now, big thick piece of wire over here. We take this thing and we connect it to some kind of a battery. Okay, like this. Good. Very nice. That's how you can create a charge difference. And because of this charge difference, the electrons are going to want to move. And where are they going to be attracted? Well, they're going to be attracted towards the positive direction. They still have random motion. They're still bumping around into this lattice in various ways. But now there's just a kind of average drift to the right. Things are roughly generally moving to the right-hand side now. So this results in an average, sometimes called average net, a net movement slash velocity towards the positive end. Okay, and now this average flow, I'm pretty sure this is AS. Can't say for certain, can't quite remember, but almost certain it's AS. This average flow is called the current. So this is this flow that we were mentioning before that we gave the symbol I. It's not all the motion of the electrons, it's just the average motion of the electrons. All this random stuff, we don't care about it. Okay, good. So this was all words, and now we can put maths to these words. And putting maths to these words, as I mentioned before, is just on syllabus for EdXL and OCR, but not for AQA. but I think it will still be useful anyway, if you're an AQA, to understand this. So we're going to take a piece of wire. Is it not the drift velocity? Yes, you're absolutely right. In fact, let me just write that now as well. Let me call it that. This average velocity gets the name, the drift velocity, because it's like the direction in which all of these electrons are drifting. Good. Okay, so now we're going to put this in an equation. So let's imagine we have this wire, and there are some things we know about it. We know the area of it here. We know the number, right here, we know the number of electrons or number of charges per volume. This often gets just called the electron number density. Good. We have the charge of a single charge carrier, which is usually the elementary charge because it's usually electrons that are moving around our circuit. And we have this velocity that we were talking about before, which is indeed called the drift velocity. So it's not the total velocity of any individual electron, it's the average velocity of all the electrons. So if we take all of these quantities, this is the area, the cross-sectional area, which we have here. We take all of these quantities and we multiply them together, we actually get back the current. And assuming we did everything on the right-hand side in standard units, this current will be in amps. Amperes, that is. Good. And we can just have a little think about this equation. What's this saying? This is saying if we increase the number of charges we have, so let's say this is one material like this. Let's say we add in, let's say we double the number of charges. Here's a load more charges. Well, then we're going to get more current flowing. This makes sense. So that's what this number density is doing. You used a Q instead of an E. Yeah, that's going to come up in one of our exam questions. The reason why people sometimes use a Q is because very rarely, but sometimes, the things carrying charge that are free to move are not electrons. And there's some other weird charge with some other actual charge Q. So you are right. If the things moving through, if the things causing the current are not electrons, then this thing would instead be replaced with just a symbol Q. And we're going to see that in one of the exam questions. Yeah. Good. Okay. And that's why it's kind of here in this equation. If you increase the amount of charge on each charge carrier, you would increase the current. If you increase the velocity, you would increase the current. So that's why it's in there. And that's the whole thing. That's why all these symbols are in there. So this is a super useful equation. Just a little bit more. This mean drift velocity, as we were saying before, this thing is the slow average velocity. Average velocity of the electrons, or in general of the charge carriers of the electrons. Good. This electron number density is the number of free electrons per volume. And in the case that you are asking about, the word electrons would be just replaced with the word charges, in case you had some other Q instead of E. Okay, so if the number of free electrons is given the symbol capital N and the volume of our wire is called V, then this electron number density, we give that the symbol little n, as we did here. Good, okay. So at this point, we're going to go through some exam questions. So before that, how's everyone feeling? One, nice, okay. Again, if this feels a bit unfamiliar, especially if you're AQA, that's okay. AQA, you don't need to know this last equation. By the way, I don't think I gave it a name. Oh, well, we have the title here. This equation, I equals A N E V. This is the transport equation. That's just the name for this equation. Okay, so I don't see any other questions at the moment. So just let me know if there are any. In the meantime, we have some more substantial exam questions to do here than in the first half. So the wires connecting a 36-watt lamp to a 12-volt battery are made of copper. Okay. They have we should label these quantities as we're reading it. This is really good practice. Watts, what's that? Watts are a unit of power. Volt, battery, well, we usually give that the symbol, well, capital V for volts. Copper, they have a cross-sectional area. Okay, let's give that a symbol A. 1.1 times 10 to the minus 7 meters squared. The current, well, that's an I, is 3 amps. The number of free electrons is this. We usually give the number per volume, per meter cubed here, the symbol little n. You see that if you label the quantities as you read the question, you immediately get an idea of what equations you might need to use. So describe what is meant by the term mean drift velocity of the electrons in the wire. So we talked about this a few times, so I'll just jot it down. It is the slow, just as we said before, the slow average velocity of free electrons as they progress through the wire. Good. Okay. Calculate the mean drift velocity, V, of the electrons in this wire. What equation should we use for this? What equation should we use? Again, the symbols that we've had to write down just to read the question should give us a hint here. Indeed, it's going to be the transport equation. It's going to be I equals, good, absolutely right, A N E V. Good. And you're right. They've said about electrons, so I'm happy just to put E. In general, you could have put a Q. Good. Okay. They want this thing, so let's rearrange for it. V equals I over A N E. Do we know the current? Yes, they told us it's 3.0 amps. Do we know the cross-sectional area? Yes, it's 1.1 times 10 to the power minus 7. Do we know the number of free electrons per meter cubed? Yes, it's 8 times 10 to the 28. That's a massive number. 8 times 10 to the power 28. Do we know the charge of an electron? Yes, we always know that. 1.6 times 10 to minus 19. They didn't give us it in the question, but it will be in the formula book, and that's really one that you should memorize anyway. Good, okay. Let's put it in a calculator. And if we put it in a calculator, you should get around 2.13068, etc., times 10 to the power minus 3. So that's roughly 2.1 times 10 to the minus 3. They gave us everything to 2 significant figures, so we give it back to the same number of significant figures. Good. Do we use 1.6 or minus 1.6? That is a good question. I used 1.6 here. It doesn't really matter here. After all, they didn't tell us, they didn't give us like a diagram of how this circuit is even set up in space anyway. So saying the velocity is positive or negative doesn't really mean too much for them here, and they're not going to be worried about that in the answer. And so in that case, you want the final velocity to be positive. And so I just chose the numbers so that that worked out. Yeah, if that makes sense. Very technically, you should probably use minus 1.6, but it absolutely doesn't matter here. Good. It only matters if you care about the direction of the velocity. Yeah, good. Okay. The current I in a conductor of cross-sectional area A is given by the formula I equals NAQV. So this is this version that you mentioned in the chat before, where Q is the charge on a charge carrier. So here, the things that are drifting through the wire causing a current might not be electrons, but they almost always are. What do the quantities N and V represent? Well, N before was a number of electron density, it was a number of electrons per volume. Here we should just say it is the charge number density. Charge number density. You could also have just literally said it's the charge per volume. You don't need to know this name. You can just say, exactly right. Charge number, charge carrier. You can also just say literally it's the charge per volume. Good. Of 3 charges. Of charge carriers, if you like. Okay, V. V is the mean or average drift velocity. Mean is really redundant here. You can just say drift velocity because drift velocity already means a mean velocity. Okay, a student has a metal conductor and a plastic insulator of the same dimensions. This is a good question, this one. So we have 2 identical materials, metal conductor and plastic insulator. Fine. And they're exactly the same. But one is metal, one is plastic. Okay. He applies the same potential difference across each. Explain how the relative values of N for the metal conductor and the plastic insulator affect the current in each. Okay, this is a really good question. So first of all, let's imagine actually attaching some potential difference. Doesn't matter what it is. Say it's 5 volts. Who cares? Okay. They're asking how N will affect the current in each. Let's start by asking ourselves, what's the current going to be in each? When is the current going to be higher, for the metal or for the plastic? And then we can backdate and think about what's causing this difference at the level of the charge carriers. Good. We know if we put metal in a circuit, current's going to flow nicely. Plastic is an insulator. It's going to block the flow of current. Okay. So we have bigger current in the metal. Now they want us to explain that in terms of the number N. So if we look at this formula, we see that I equals A, well, they wrote it like this, NAQV. So a material with a larger electron density N will allow a larger current. And then just to piece this together, we should say which material actually has this. Metal is a conductor, so has a larger N. And that does it. Good. Okay. So that's a nice question. You actually see now an equation that shows you the difference between conductors and insulators. The difference is in this number N, and it's right there in the equation that tells you how much current is going to flow. This is really pretty. Okay, last question. The student connects two pieces of copper wire, A and B, in series with each other and the battery. Okay, we should draw this. This is a good question, but it's definitely the hardest one that we'll have looked at, especially if you don't like algebra. So we have two pieces of copper wire, A and B, in series with each other in a battery. Diameter of A is twice that of B. So here's A, big piece of wire, and here's B, piece of wire with a smaller diameter. Okay, good. Now what? The diameter of wire A is twice that of B. Diameter of A equals 2 times the diameter of B. In other words, the diameter of B is diameter of A over 2. Okay. Calculate the ratio of the mean drift velocity in wire A to the drift velocity in wire B. Looks like they've given us almost no information. Okay, they want us to know how the velocity of things moving through here compares with the velocity of things moving through here. Clearly, they believe it's going to be different because of these different diameters. What equation is going to allow us to figure this out? What equation relates drift velocity and things a bit like diameter? Well, diameter is kind of thing you can use to calculate cross-sectional area. So the equation that they want us to use here is absolutely this transport equation. It is I equals N A Q V. And we can replace the cross-sectional area now with the diameter. Note that area is pi r squared. So that's pi times the diameter over 2 squared. So it's n times pi times diameter over 2 squared times q times v. Okay. Now the problem is we've got two materials here. So we're going to have to write down the transport equation for each of them. So we know that the current through our first material A is going to be the number density in A times pi times the diameter of A over 2 squared times the charge of each charge carrier in A times by the velocity in A. And the current in B is going to be the same. Now, what can you tell me about the current through these two materials in this experimental setup? Because this is way more variables than they told us about. So some things are going to have to end up being equal. They're going to have to end up cancelling out in some nice way. What's happening here? What's the relationship between the current in wire A and the current in wire B? Good. And why is it the same? Because these are components in series in a circuit, and we haven't talked about it here, but any components in series in a circuit will have the same current flowing through it. So in fact, we have the NA pi. This means that IA is IB. So NA pi dA over 2 squared QA VA equals NB pi dB over 2 squared. Much more algebraically heavy question. Okay. Now, this still has stuff that isn't in the question. They told us about the diameters, so that's okay. We're being asked about the ratio of the velocities, so we can keep the velocities there. But what are we doing about the N's and Q's? So we have two pieces of copper wire, so they're the same material. So the thing that we need to know here, good, yeah. The number density, the number of free charge carriers per volume in a material, that is a property of a material, not a particular object. So any piece of copper will have the same number density of carriers. So actually, Na equals Nb. Good. And the kinds of charges that carry current are going to be the same in both wires because they're both made of the same material again. In this case, QA equals QB. And it's just electrons in copper. It's just a conducting metal. So this is E anyway. So there's loads of stuff we can cancel out. We can cancel the N's because Na is the same as Nb. We can cancel the Q's because Qa is the same as Qb. We can cancel the pi's because pi is the same as pi. And now we've suddenly got something way more manageable. Okay, what did they actually want? The ratio of the velocity in A to the velocity in B. So they want VA over VB. So let's just rearrange what we have for that. So we have this thing squared times this is this thing squared times this. I'm going to divide both sides by VB and divide both sides by dA over 2. So we have VA over VB equals dB over 2 squared over dA over 2 squared. Those twos are going to cancel and you're just going to get dB squared over dA squared. And that is actually the final answer. They wanted us to calculate the ratio of these two things. We know the ratio dB over dA. Why? Because it's here. dA equals 2 dB. They told us diameter of wire A is twice that of B. So dB over dA is actually 1/2. Yes, that's the right way around. It's 1/2. So this is the same as 1 over 2 squared, which is 1 over 4. So final answer, VA over VB equals 1 over 4. And that's our final answer. And a really cool question. It's definitely among the harder ones you would do in A level, just because of the amount of algebra. Of course, I took my time to explain it. You could do it quicker than this in the exam, but you need to have seen this kind of argument once, and then it will be quicker each time. Okay, good. So you should now be able to define the terms charge and the term current. You should understand that charge is quantized. Charge comes in bits of size E. And you should be able to describe that current is caused by the movement of electrons. And notice there's a lot more in that third statement that meets the eye. It's not just current as the flow of charge. It's the movement of electrons is super complicated. So it's caused by this drift velocity, this average velocity of the electrons as they move around the circuit. Okay, and so that completes all the talk part of the session. We ran slightly over by a couple of minutes, so apologies for that. Nonetheless, I can keep an eye on the chat if there are any other questions, and I hope this was useful. So yeah, I'll just keep my eye on the chat in case there's any more questions. Okay, so since I don't see anything else, as long as nothing pops up while I'm wrapping up, I would simply say thanks very much everyone who came. It was really useful to have people answering the questions in the chat. I hope that this was useful for you. And there aren't just physics sessions on here. There's many other subjects that we do live streams for as well. And we have teaching materials on the Snap Revise website. So I'll just finish by saying thanks very much everyone for coming, and catch you at the next one. Okay, bye.